Hello, everyone. My name is Alghamdi. I'm a student in King Abdullah University of Science and Technology. And today I'll be presenting a work that I've been doing for not a long time. So it's not a really complete work, but I would like to share with you the ideas that I have here. So the work is about ontology alignment through graph projection, machine learning, and iterative inconsistency removal. This work is a collaboration with also one of my colleagues in KAUST, Fernando. Okay. Is there a way I can remove this?
If you remove your mouse pointer, it will vanish. It should vanish. Okay. Sure. Also, one moment.
Try and drag it up to the top of the screen.
Wait, there is a height video panel.
No, not the
No.
video panel.
Height floating meeting controls.
Yes, perfect.
Yes, and now I hope they will auto hide.
Height floating.
Yes.
Yes. Thank you so much. So as you all know, ontology plays an important role in sharing and reusing knowledge. And several ontologies have been developed from a perspective of a community of developers and users. But unfortunately, some of those communities are isolated. And when this happened, the problem of the existence of multiple ontologies that covers the same domain in a variety of different level of variation between those ontologies. And the reason for that is because of the human nature of having those different perspectives. And to solve this task, we have the ontology alignment problem, and which is the task for identifying correspondences between semantically related elements between two or more ontologies. And if we look at it from the view of having two ontologies, so basically this will be the ontology alignment task will give us a set of alignments, a class from the first ontology that is that have some score with another class from the other ontology. And the relations here are typically denoting equivalence or subsumption relations. For examples, we have ontology that represent the mouse anatomy, the mouse anatomy ontology, and we have also another ontology that represents the anatomy of the human. And as they have some differences between them, but they have some similarities that perhaps does not really give us an equivalence relation. But if we want to, for example, see the effect of a gene change or a drug between what we have in a mouse and the human, we can define those similarities between, for example, the lung of both the mouse and the human, and the heart and the liver. And also, if we look at for example, the mammalian phenotype ontology and the human phenotype ontology, we can find some similarity between the classes that we have here. So we have, for example, the hearing loss in both ontologies. The state-of-the-art alignment approaches basically cover those main approaches. So firstly, most of them basically do some lexical alignment, and they use different ways to do this. Maybe they use resources out of the ontologies, like terminological resources, like dictionaries and so on, and language-based techniques and text matching methods. Also, they use formal resources. So some of the approaches, some of the state-of-the-art aligned approaches use background knowledge from other ontologies, or use the taxonomy of the ontology, or use the instances of the ontology. So basically, the using the ABOX of the ontology, and some of them use some structuring matching. So basically, matching the ancestors and the descendants, looking at the similarities between those by using the subsumption relation in the ontology. And yes, for maybe the top of the state of the art, if we look at AML and LogMap, for example, they use logic-based mapping repair. So at the end, they have a way to repair the mappings by making sure that the alignments are consistent. And however, none of these previous methods have explored the use of inconsistencies to inform the learning. So it's used by a way of preparing the found alignments, but not in the process of the learning using machine learning algorithms. And limited of those methods have used axioms from the ontologies other than subsumption relation. And what I mean here is the axioms that are relating to the logical axioms. So the disjointness, the intersections, the existential and the universal classifiers. So what we are proposing here is an alignment that utilizes ontology's rich axioms and logical inferences in a semi-supervised way. And we do that following these steps. So at the beginning, we start by learning some lexical matchings, and the reason we want to learn that is just we want to have initial seeds that we will carry on as if it's a way to learn those start seeds, but without having to have the references given. So it's a way to have it as a semi-supervised way. And the second way, the second point is by projecting the ontologies into graph representations. And here, in this graph representation, we are using a similar projection to out of X star. And in this projection, basically, what they do is that they use all of the logical axioms in the ontologies, including the intersections and the union, the existential quantifiers, and and also well, they do create some sort of a graph, and this graph we cannot go back from this graph to the axioms, but the main idea of having this graph is to be able to reach to the similarity between the classes that shares some relations with other classes from other ontologies. And here I give you just an example of how we could have some kind of relation between different ontologies by the classes that they share in the graph. And this is just not the complete graph, but just a small a view of the graph. And then we learned some transformation. So we apply here machine learning transformation. And the main idea here is that we will be projecting each of these ontologies to a different embedding space. And then we try to learn this alignments between the classes from the ontologies by basically trying to minimize the difference between those classes by transformation, by applying some kind of transformation. So basically, you can imagine that what we're doing here is that if we are having those embedding spaces, we're trying to find a transformation that align the classes together, and hence we can be able to find classes that are not yet found by the lexical matcher that we started with. And just if you can, this is inspired by the entrance-E model, which was applied with knowledge graph alignment. But what we do here is we apply it in a fashion that is like mtrans-R, where we have different weights for each of the relations, of the different relations. And then basically we add a step of checking the consistency of the alignment. And to check the consistency of the alignment, basically we have to merge both ontologies and add equivalence class axioms between the alignments that we have predicted at this point. And after that, we check the source of the inconsistency of these alignments. And what we're doing here basically is we're trying to find the alignments that causes the most number of inconsistencies from those equivalence classes that we have defined. And after we find them, we remove them from the alignment and we add them as a true negatives. And we retrain, then in the next step, we retrain going to the transformation learning with adding this additional loss. Basically, instead of only looking at the positive alignments that we have, we also add a loss for the negative alignments that we found that causes these inconsistencies. Or if the ontology is consistent, then we return the alignments that we have found. For evaluation, we didn't evaluate this extensively in ontologies because most of the ontologies that we have didn't have much of disjointness that can find this can be found by the matching that we have. So here I applied this on the human phenotype ontology and the mammalian phenotype ontology from last year's Ontology Alignment Evaluation Initiative dataset that reference that they provided, the consistency of the participating methods. And here I'm showing the results that I found in the competition. So I took the alignments and applied the same evaluation method that I applied on my tool, but I didn't generate it. So I took the alignment provided by the initiative. And here I show you the results. It's not the best results that we have here. So still LogMap and Agreement Maker Lite are getting the highest results, I guess. But what we found here is that we did generate some comparable results to LogMap and AML. And as a summary, we proposed an ontology alignment method that learns the alignment by collective of lexical, semantical, and logical reasoning approaches. By iteratively correcting the inconsistency, we demonstrate that our method produce consistent alignment, and our method overcome the scalability issue by learning the representation of the ontologies through the graph projection that I have showed you. And the transformation learning we applied allowed to learn the global information from each ontology separately, as well as this kind of transformation that allows us to find more alignments more indirect alignments that can only be found by lexical matching. And yes, and that's it for the presentation. Thank you for listening.
Time for some questions, please.
So what are your next steps to improve your alignment?
Well, basically, currently, we're still trying to fine-tune the parameters that we have. So basically, we are doing it's the trade-off between how much would you train and how much would you train with the without the inconsistency negatives and with the inconsistency negatives. And we want to also analyze basically how each of these, we have several components in this method, and we want to find which one of these components is contributing best to the ontology, to the alignment finding.
Just please repeat the question for the online audience.
What was it? Yeah. So I got the question of what was the next step, and this was my answer.
I thought wonderful presentation, and I really like the methodology. It's very inspiring.
Thank you.
So I have two questions on the transformation learning.
Yes.
First question is, yeah, this is a question. So it's both. You have this mapping from the graph projection to the embedding state. There are two mappings happening, right? From the ontology to the graph to the space. You kind of assume, I suppose, that your mappings are final or optimal, especially towards the embedding space. What I found, the reality is often you have just one embedding. You're fine with the suboptimal solution, right? But if you would have this kind of comparison, you kind of require that you have a optimal. Because if you run this again with different random seeds, you'll get a different embedding. No?
Well, yes. I have to first fix. Maybe I passed by this fast, but we don't first map it to the embedding space and then learn the alignment. We do this simultaneously. So each epoch will learn from the knowledge graph, the first knowledge graph, then the second knowledge graph, then from the alignment, and then this is happening simultaneously. So even adding the inconsistency negatives is also happening simultaneously. We keep in each epoch training each of these parts. So it's not a separate step.
It kind of answers my second question, I think, which is the transformation or the alignment step.
Yes.
What kind of transformations do you allow? It's linear and rotation, or what?
It's only yes. So what kind of transformation are we learning from the alignment step? From the alignment step, it's only a transformation. I don't add any.
Only transformation.
Yes, I don't add any.
No.
I was just going to ask that in your step where you're checking the logic consistency of the mappings.
Yes.
You mentioned, I think, asserting equivalent class axioms. Do you possibly learn that one may be a subclass of the other, like they're closely related, but one ontology is more specific?
This is an next step that I want to apply. Yes. So the question is whether in the consistency check step, are we learning from the subclass axioms, or are we predicting the subclass relation between the ontologies? And the answer is no, not yet. But it's one of the things that I want to also explore.
We have time for maybe one more question.
Yes.
Yes, mine was actually very similar. I was interested in you talk just a bit more about the detecting inconsistency. Did you add any of your own disjointness axioms? And I missed, did you manually check the inconsistencies, or is that part of the algorithm?
No.
Look at the inconsistencies and remove them?
Did I manually check the inconsistency or it's part of the algorithm? It's part of the algorithm. I'm sorry, I also didn't write it here. I should have written it here.
Very good.
So yes, basically, first I start by merging the ontologies, and then I'm at the equivalent class axioms for those predicted based on our transformation function. So I use this function that I have optimized to learn whether I find a class that I multiply by this matrix that I have learned from the first ontology minus the other class, and I'm looking for the minimum distance. And based on a threshold, I predict several alignments. I add those alignments as an equivalent class axiom to this merged ontology, and then I found I try to find the inconsistencies. Well, I add first the equivalent class axioms, and if I can find those unsatisfied classes, I try to query the cause of this, and well, the what is it called? I use elk reasoner here to find the explanations, yes, and whether the explanation have one of these axioms that I have defined, those equivalent class axioms that I have defined. If I find it, then I start counting which of those, how many unsatisfied classes each of those axioms have. And then I start removing the ones that produce the most number. This is inspired by actually another very interesting paper that was published before, where they were in this paper trying to find the hidden inconsistencies in OVO ontologies, and using the similar method to what they did. We try to incorporate this by finding which of those equivalent class axioms produce the most number of unsatisfied classes and remove them. Once we reach to a consistent merged ontology, then we stop. And those are added as a true negatives the next round. I don't know if I should say true negatives, maybe inconsistency negatives would be a better name for this.
Okay, do we have an online question, perhaps?
We hide this.
Okay, maybe.
Okay.
I
No.
think that.
Okay, so in this case, since we have no more questions, please let's thank all the speakers of this session again.